Hello, and welcome to our RSS 2020 talk on optimally assigning robots to a stream of incoming tasks while accounting for uncertainty and time constraints. Efficient and high-quality task allocation is crucial for applications with multiple robots working together, from logistics to manufacturing to services. Consider two real-world examples here. Warehouse operations involve a team of robot arms collaborating on an assembly line, and on-demand delivery services dispatch drones to incoming package delivery requests. Multi-robot task allocation needs to be computationally efficient and produce good solutions while accounting for the characteristics of real-world robotics, all of which manifest in this repeating segment. The imperfect grasping by the arm induces task execution uncertainty. The workspace limits along with the moving conveyor belt induce time window constraints for completing the task, and new tasks appear online as objects placed on the belt. The robot team's objective here is to minimize the expected number of task failures at the end of the operation horizon, in this case to minimize the number of missed objects that must be sorted by hand afterwards. Our key idea is to decouple the algorithmic challenges of sequential planning under uncertainty and multi-robot coordination and address them at separate levels. In contrast, prior works attempted the intractable joint problem and required simplifying approximations or heuristics. We decompose and recombine in a manner that circumvents some complexity without sacrificing solution quality. Our hierarchical two-level algorithm proceeds as follows. At the lower level, it plans independently for each robot and subset of reachable tasks to decide the single robot allocation policy. It uses dynamic programming over policy tree search to reason about the probability of successful task completion within the time windows. For example, for robot N1 and objects K1 and K2 here, the tree encodes whether to attempt or to leave K1 and then attempt or leave K2 with some branch-dependent outcome probability. Since the lower-level tree searches are run separately per robot, also for N2 and N3 and so on, conflicts may arise due to multiple robots attempting the same task in overlapping windows. Breaking such ties arbitrarily could yield poor quality allocations. Therefore, at the higher level, our algorithm coordinates the allocation policies of each robot using optimal conflict resolution logic adapted from the path planning community. The higher and lower levels work repeatedly to obtain a conflict-free multi-robot allocation. Our algorithm, Stochastic Conflict-Based Allocation or SCoBA, is optimal in expectation and complete under mild assumptions and can interleave planning and execution online for new tasks. To evaluate SCoBA, we set up two distinct robotics-inspired simulation domains from earlier: conveyor belt pick and place and multi-drone delivery dispatch. In the interest of time, I'll only discuss our results for the primary performance metric, minimizing the number of task failures at the end of an operation horizon. We baseline SCoBA against a range of multi-robot allocation approaches from scheduling, such as earliest due date and the Hungarian algorithm, and from sequential decision-making, by framing it as an MDP and applying Q-learning and Monte Carlo tree search. On the conveyor belt domain, where our metric is the fraction of objects missed by all arms, we find that SCoBA outperforms all baselines, that is, misses fewer objects than the baselines do. The performance gap is consistent across three varying system parameters that all affect the problem difficulty in different ways. On the multi-drone delivery domain, where our metric is the fraction of late package deliveries, we find that SCoBA mostly outperforms all applicable baselines, once again with varying system parameters. However, its performance gap over the MCTS baseline is reduced, as this baseline is tailored for vehicle dispatch problems. The paper has additional results on computation time and competitive performance against an oracle with lookahead. In summary, we introduced a hierarchical multi-robot task allocation algorithm that accounts for uncertainty, time constraints, and new tasks arriving dynamically. Future work could look at stochasticity at the conflict level and lifting the assumption of known uncertainty models. Please see our extended version on arXiv and open source code as well. Thank you for your attention.